Hey everyone, I hope you're doing well today. In this video, I'm going to be talking about how to solve differential equations by using the method of separation of variables. Real quick, before we begin, I just want to give a huge shout out and a big thank you to the Hawes family for sponsoring this video. Thanks to their donation on my GoFundMe page, they made this video possible. If you weren't already aware, I'm starting a program where 100% of all donations and proceeds will go back towards educating children. If you're interested to learn more, feel free to check out my website at www.simplified.com. And while you're at it, feel free to click the like button to help you get better at math. Alright, let's talk about this topic now. We use the separation of variable strategy to solve differential equations when we can move all the y terms including dy to one side of the equation and all the x terms including dx to the other side of the equation. Whenever you find you can do this, you can use the strategy of separation of variables. Here are some quick bits of information that are going to be helpful throughout this video. First, it's important to know that y prime is the same thing as dy over dx. These can be substituted for each other. Next, it's important to know your log properties. It's important to know that ln of e is equal to 1, e to the ln of x is just equal to x. If you have a base with a sum of exponents, you can separate it into a product. And when you have a base with a difference of exponents, you can rewrite it as a quotient. It's important to remember that we're going to have different types of constants, but they all boil down just to being the general constant. And finally, here are some integrals that will help you solve each of these differential equations. While the information on the screen isn't everything you need to know to solve the equations, it should help you a good amount. Now that we've gone over some background information, I encourage you to grab some paper and something to write with. Feel free to practice alongside me, and let's do some math together. In this first problem, we have the differential equation y prime is equal to 4 times x times y squared. The y of 0 that's equal to 1 is what we call our initial condition. Later on, once we find our general solution, we can use this initial condition to find out our constant or our c value. But for now, we're just going to ignore it because we don't really need it yet. Let's start by rewriting our y prime as dy over dx. Now to get all the x terms including dx on one side and to get all the y terms including dy on the other, we can start by multiplying both sides by dx, then multiplying both sides by 1 over y squared, or dividing both sides by y squared. In doing so, these dx's are going to cancel out on the left side, and these y squareds are going to cancel out on the right side. From that, we're going to get 1 over y squared dy is equal to 4x dx. Notice how we've now separated all the y terms on the left side, and we separated all the x terms to the right side. And that just might be where the super original name of separation of variables comes from. Now that we have them separated, let's take the integrals of both sides. Using our exponent rules, we can rewrite 1 over y squared as y to the negative second power. Taking the integral of the left side, we'll get negative 1 over y plus c1. Remember that when you're integrating y to the negative second power, you're actually just going to add 1 to its exponent and divide that by negative 2 plus 1. When you do that, you're going to get y to the negative first power over negative 1, which is the same thing as negative 1 over y. Now for integrating the right side, we're going to get 2x squared plus c2, or our second constant. When integrating 4x, keep in mind that we have an exponent of 1, and we're going to add 1 to it, and then divide that by 1 plus 1. This will get us our 4x squared, and this is going to be over 2, which just simplifies down to 2x squared. Now that we took our integrals, we can combine our constants by subtracting c1 from both sides to get them both on the right side of the equation. Since any constant minus another constant is just another constant, I'm going to say that c2 minus c1, I'm just going to call that c. Now let's continue this up here. Since we're solving for y and it's in the denominator, I'm going to rewrite the 2x squared plus c over 1 so that we can flip both sides of this equation. Taking the reciprocal of both sides, we can write negative y is equal to 1 over 2x squared plus c. And multiplying both sides by negative 1, we find that y is equal to negative 1 over 2x squared plus c. This right here is our general solution. And now let's take our initial condition of y of 0 is equal to 1 and substitute it in for x and y to solve for c. Substituting in, we get y is equal to negative 1 over 2 times 0 squared plus c. And since 0 squared is 0 times 2, which is still 0, we can say 1 is equal to negative 1 over c. So we can say that c, or our constant, is equal to negative 1. Taking this negative 1 and substituting it in for c, we get our final equation of y is equal to negative 1 over 2x squared minus 1. And just for a couple key takeaways, when you're given an initial condition, you don't actually need it until you find your general solution, so just hold that off for later. Once you've ignored your initial condition, work on separating your variables on the left and right side. Then you can integrate and don't forget you'll have a constant. And if you feel comfortable just writing 1c as a constant since you know they're going to combine, that's also okay. Then you can just use some algebra to rearrange the equation to isolate y, use the initial condition to find c, and then you'll have your particular solution given that initial condition. Let's try another here. Our equation is y prime is equal to x times y. We have an initial condition of y of 0 is equal to 5, but we'll deal with that later. Let's start by rewriting y prime as dy over dx and then separate the variables to the left side and the right side. First, we can multiply both sides by dx, so the dx's will cancel out on the left side. Then we'll multiply both sides by 1 over y, or divide both sides by y, so these y's cancel out on the right side. By doing so, we get the y term and dy on the left side, and the x term and dx on the right side. Now that we have them separated, we can go ahead and take the integral of both sides, and for the left side, we're going to get ln of the absolute value of y plus a constant, and for the right side, we'll get x squared over 2 plus a second constant. Keep in mind that after you integrate, you can always find the derivative of your integral and see if you get the same thing that you started with. So if you took the derivative of this ln of y, you're going to get 1 over y, so we know we did this correctly. Similarly, if you were to find the derivative of x squared over 2 and perform the power rule, you're going to get x, which is what we started with. Now to combine our constants, we can subtract c1 from both sides. And combining our constants, we're going to get ln of the absolute value of y is equal to x squared over 2 plus c. As you practice more problems, you'll get more used to the fact that our constants always combine just to make one general constant. Now let's work on isolating y. To isolate y, we're going to have to exponentiate both sides with a base of e to cancel out the natural logarithm. Using our log properties, we can take this absolute value of y and bring it out in front, and this e to the ln will cancel out to make 1. Using our product rule of exponents, we can rewrite this e to the x squared over 2 plus c as two different powers, both with base e. Since e is just a constant of about 2.718, we can simplify a constant raised to another constant as just a general constant of c. Just rearranging the right side to put our constant in front and dropping the absolute value on the left, we can write y is equal to plus or minus c times e to the 1/2 x squared. That's our general solution. Keep in mind that we need the plus or minus on the right side since we had an absolute value. Now that we have our general solution, let's use this initial condition to find our constant. Substituting in 0, 5 in for x and y, we'll have 5 is equal to c times e to the 1/2 times 0 squared power. Our exponent simplifies down to 0, so we'll have 5 is equal to c times e to the 0th power. E to the 0th power is equal to 1, so we know that our constant is equal to 5. Substituting this 5 into our general solution, we find that y is equal to 5 times e to the 1/2 x squared power. And just a quick recap, start off by ignoring your initial condition, separate your x's and y's, integrate both sides, don't forget your constant, do a bit of algebra, which included exponentiating to find your general solution, then use your initial condition to find your constant, and you'll end up with your specific equation. Here's example 3. We have y prime times cosine squared of x is equal to e to the 3y power. For now, let's ignore our initial condition and let's focus on separating our variables. To get all our y terms on the left and our x terms on the right, let's multiply both sides by dx to cancel out the dx's on the left. Then multiply both sides by 1 over e to the 3y power, or divide both sides by e to the 3y power to cancel these out on the right. And finally, multiply both sides by 1 over cosine squared of x to cancel these on the left side and move it over to the right side. After rearranging and cross-canceling a bit, we have 1 over e to the 3y power dy is equal to 1 over cosine squared of x dx. To make the left side easier to integrate, I'm going to use our negative exponent rule and rewrite it as e to the negative 3y power. And using our reciprocal trig identity, we can rewrite 1 over cosine squared of x as secant squared of x. Now let's take our equation and integrate both sides. For the integral on the left, we can use some u substitution and let u equal e to the negative 3y power, which means du using the power rule is going to be negative 3 times e to the negative 3y power. Rewriting this, we can write negative 1/3 times the integral of u du. And don't forget to write this negative 1/3 because of the negative 3 in our du. And don't worry too much about the right side since we can find the integral of this pretty easily. After integrating on the left side, we're going to have negative 1/3 times e to the negative 3y power plus a constant. And on the right side, we're going to get tangent of x plus another constant. Subtracting our c1 from both sides, we can write Negative 1/3 e to the negative 3y power is equal to tangent of x plus c2 minus c1. And combining our constants together just to write a general constant, here's our general solution. Now that we have our general solution, let's use our initial condition to write our specific equation. Here's our equation when we substitute in 0, 0 for x and y. And this negative 3 times 0 just simplifies down to 0 for the exponent. And tangent of 0 is equal to 0. You want to remember on your unit circle that tangent is just going to be y over x. So when you're at 0 degrees, that's located right over here along the x-axis, the y value is 0 and the x value is 1. So 0 over 1 is just 0. And on the left side, since e to the 0 is just equal to 1, we can say that given our initial condition of 0, 0, our constant in this case is going to be negative 1/3. Now let's take this negative 1/3 and substitute it into our general equation to get this equation here. Now let's just use some algebra to rearrange the equation to solve for y. Let's multiply both sides by negative 3, and we'll get e to the negative 3y power is equal to negative 3 times tangent of x plus 1. Next, to cancel out the e, we're going to have to take the natural logarithm of both sides. And in doing so, this negative 3y can come down in front. And since ln of e is just equal to 1, we can write negative 3y is equal to the natural logarithm of 1 minus 3 times tangent of x. And finally, dividing both sides by negative 3, our equation is y is equal to negative 1/3 times the natural logarithm of 1 minus 3 times tangent of x. And just a quick recap, ignore your initial condition to start. Separate your variables. If you can, rewrite them in a form that's easier to integrate. Go ahead and integrate and be sure to use substitution when it makes your life easier. Don't forget about your constants. Get your general solution. Use your initial condition to find c. And rearrange as necessary to solve for y. Something that we did that was slightly different in this example was the fact that we used our initial condition before we solved for y. While you can solve for y first and then use your initial condition, sometimes algebraically it's easier to substitute your initial condition in before you solve for y. Notice how in the general solution that I boxed here that we didn't solve for y yet. It's more useful to solve for c here because it's alone and there's no functions attached to it. Try to keep a lookout for these types of equations where solving for your constant might be easier before you solve for y. And here's one last example. We have y prime is equal to 3 times x squared times a quantity of y squared plus 1. Our y of 0 is equal to 1 is our initial condition, but we'll deal with that a little bit later. Let's start by rewriting our y prime as dy over dx, then work on separating our variables. To get all our y's on the left and our x's on the right, let's start by multiplying both sides by dx to cancel them out on the left side. Then multiply both sides by 1 over y squared plus 1 to cancel them out on the right side to get it over to the left. By doing this, we'll get this new equation with all our y terms on the left side and all our x terms on the right side. Now let's take this equation and integrate both sides. Integrating the left side, we're going to get inverse tangent of y plus a constant, and integrating the right side, we're going to get x cubed plus another constant. And again, if you want to check this, the derivative of the inverse tangent of y is going to be 1 over y squared plus 1, and you could take the derivative of this x cubed and you'll get 3x squared in the integral. Now let's just rearrange our constants and move them over to the right side, and we can just rewrite our c2 minus c1 as just a general constant c. Continuing this over here, we can take our entire equation and take the tangent of both sides since we have an arctangent. On the left side, tangent of arctangent of y will just simplify down to y, and we can write our general solution as y is equal to tangent of the quantity of x cubed plus our constant. Now let's use our initial condition to find the value of our constant. Now try to remember what I said in the last example. While you could use the initial condition to find the value of c using this general solution, it's actually going to save you some work if you use the equation above, since there's no function attached to our constant here. Substituting the initial condition into that equation, we're going to get arctangent or the inverse tangent of 1 is equal to 0 cubed plus c. To figure out inverse tangent of 1, it might help to look at this 45, 45, 90 triangle. What you have to ask yourself is tangent of what angle gets you a ratio of 1? Since that's equal to 45 degrees or pi over 4 in radians, we can write pi over 4 is equal to 0 plus c. That means we found our general constant to be pi over 4. Let's take this pi over 4 and substitute it into our general solution where we already have y isolated. In doing so, we're going to get this final equation of y is equal to tangent of the quantity of x cubed plus pi over 4. And again, here's one final recap. Whenever you get started, don't worry about the initial condition, you can deal with that after you find your general solution. Then go ahead and use your algebra skills to separate your variables until you have all your y's and dy's on the left and all your x's and dx's on the right. Once you do that, you can integrate. If you didn't know that the derivative of arctangent of y was equal to 1 over y squared plus 1, it would probably be pretty difficult to know that the integral or the antiderivative of 1 over y squared plus 1 would be the arctangent of y. Either way, make sure you either have a chart or a table in front of you with your integrals or derivatives, or just simply memorize them. Then as usual, combine your constants, and try to isolate y to write your general solution. If your general solution has your constant in a weird spot that makes it hard to solve for it, feel free to backtrack to an earlier equation where it's a little bit easier to solve for c. Then use your initial condition to solve for your constant, draw some triangles or a unit circle to help you with some trig functions, solve for your constant, and substitute it into your general solution. And that wraps up this video on a few examples of solving differential equations by separation of variables. If you found this video helpful at all, please consider giving it a like and maybe even subscribing so you can get more content in the future. Once again, I wanted to say a big thank you and a shout out to the Halls family for making this video possible. And if you'd like to find out more about my mission, feel free to check out my website again at www.simplified.com. As always, keep up the good work, and I'll see you in the next one.